All right, welcome back. We will start our first hands-on session, Intro to P4 and BMv2. I want to mention that the PowerPoint slides in two formats, PDF and PowerPoint, are available. And there is some links. If you didn't register yet, we will be using a virtual platform. So in slide number 14, there is an URL to register to the platform. This is the same URL that was sent last week. If you did register, you can reserve time and you will have the pod deploy when I mentioned that before we start. So this slide again are already online. Hands-on session number 1. So this hands-on session is about an intro to P4 and BMv2. And before we start, I wanna mention again that we are gonna be using BMv2. This is a software switch that is open source, typically used for teaching, researching ideas, good to validate new ideas, research ideas. This lab library contains 8 labs. We will just do 2 here. From an intro to Mininet, we will be using Mininet. The BMv2 switch will be integrated to Mininet. Then an intro to P4, BMv2, all the way to lab 6, 7, populating, managing match action tables, and packet parsing. So these lab experiments include step-by-step directions. So the idea, as we said at the very beginning, is that these lab libraries are used for associate bachelor all the way to grad level. And then there are some challenges, exercises. They don't have directions, but they are also included in the virtual machine. Before I continue, I want to mention also, I think I forgot, in our website, there is a table, resources. We're using one virtual machine, and if you wish to download this virtual machine and run on your own computer, the link to download is here in the website. For those who are not that familiar with Mininet, Mininet is a virtual testbed that contains nodes. Nodes are containers, or more specifically, they are network namespaces. It's pretty good for fast prototyping of new protocols, new ideas. Very simple to test complex topologies. It is quite realistic in the sense that it ran real code. There are BMv2. There are also hosts running Linux. Is open source, and it can run pretty large networks. We integrated Mininet with MiniEdit, which is a graphical user interface that is also linked with Mininet. Here we have an example. On the left-hand side, we have a network with 2 hosts, H1 and H2, and 1 switch, S1. On the right-hand side is the topology that we're building using MiniEdit. The panel includes several devices, for example, host devices. Let's see if we have a better example. Right here, host devices, P4 switches, SDN switches, legacy switches, routers. These are traditional routers. We use FR routing. Linux devices, I already mentioned. So it's a very rich platform. Pretty easy to manipulate the devices using the graphical user interface. Easy to, for example, assign IPv4, IPv6 addresses. Easy to test very quickly. again, using the graphical user interface with a simple right click, opening a terminal, or even manipulating the switch that we will see in the labs. We build examples using BMv2, and they are running inside Docker containers. The code is written in Visual Studio Code with a built-in terminal. On the left-hand side here, we have an example, a topology. On the right-hand side, we have a code that is going to be deployed on one of the BMv2 switches. And then at the bottom here, we have the built-in terminal. So all the environment is available right away. As I mentioned before, there are some other devices available: FR routers, OVS switches, Linux host. And this is the workflow that we will use. First, we have a P4 program, .p4. In this example is basic.p4. Then there is an architecture module. We will be using the V1 model. And this is what we would replace if we're using, for example, Tofino switches. We will use the Tofino native architecture here, TNA. We have the compiler, and the compiler generating the executable file that is going to be loaded into the data plane of the switch. The switch, the control plane interacts with the data plane using a simple switch command line interface. So that's the environment. The first lab that we will be doing here is about P4 program building blocks. We will be looking at the different building blocks as Vladimir was discussing before. And in order to do so, I want to let Elie lead to that exercise. I want to briefly introduce Elie. Elie is a PhD student here in the College of Engineering and Computing. He's working with me, has been working with me for the last 3 years. His research focuses on P4 programmable switches, network security, blockchain, IoT, software-defined networking. Some examples: he has been working here at USC, dynamic router buffering, conversational media traffic offloading to the data plane, botnet detections in the data plane, and few other projects. I want to give credit Elie also because he's one of the individuals who developed these labs. So Elie, are you there? Can you share your screen right now?
Yes, sure. Thank you, Doctor. All right. So hello, everyone. So I will go over the slides, and then we will shift to the practical part, the hands-on part. So before we do that, I will also describe what architecture we'll be using. So Vladimir was mentioning the PISA, which is the general architecture. But in our case, we're going to use an instance of this PISA, which is called V1 model. And the V1 model, first, can you see my screen?
Elie, yes, we can see your screen.
Okay.
Share this screen.
Okay, sorry for that. I was trying to share the right screen. I'm using two screens here. So basically, we will be working with the V1 model, and V1 model is a P416 architecture that is used with the software switch BMv2. And the BMv2 has a target, and this is basically the actual switch, and it has the daemon and all the executables there. It's called the simple switch. And we can see here at the bottom, this is a diagram showing the main components of the V1 model architecture. So first we have a programmable parser. Then we have an ingress match action pipeline where we have multiple stages. Then we have a traffic manager. This is the configurable component. This is not programmable. Then we have the egress pipeline. And finally, we have a programmable deparser. So all these components are programmable. Only the traffic manager is not. What we will be doing in this lab, we will go over an already written program. So we will see the different files and how they are mapped to these components. And then we will see how we can compile and then run that program on the software switch. So what we decided to do in the lab series, we decided to basically split the program, the whole P4 program, into separate files, and each file will have whatever that component is doing. So for instance, we will have a dedicated file called parser.p4. This is where we're going to be implementing all the parsing capability of the P4 switch. Then we have another file called ingress.p4. This is where we're going to be having all the tables and all the match action pipeline related to the ingress. Same thing for the egress and for the deparser, and also for the checksum verification. So I will go again over these slides. This is just the instruction to access the platform. So if you did not register yet to the platform, and this is what was sent through email, you can do so now. So there is this link. Jose, if you can please copy it to the chat. And basically you just go there, you have to fill a form, and then you're gonna receive a verification key to your email. Once you're there, you're gonna complete the enrollment, accept the terms and condition. And then once you are at that point, you'll be able to claim free access and then start by using the platform. Now, if you already registered before, all you have to do is just log in, okay? And this is the link for logging in here. When you log in there, you will see that there's a course called Programmable Switches Workshop. You just have to select the lab that you would like to do, then the reservation will start and you will be able to start doing that lab. So in our case, we will be doing lab number 3. For this lab, we have a very simple topology. We have one P4 switch and we have 2 hosts, H1 and H2. And we will see how we can compile the program, the P4 program, and then push the output of this compiler to be used as a program for the switch, right? As the data plane description. And then we will see how we can start the daemon, allocate the interfaces, and perform a simple test to verify that this program is running. Okay, so now I will shift to the platform where we're gonna start by doing the exercise. So as you can see here, I'm inside this platform. So that's the NDG platform. And here we have a course called Programmable Switches Workshop. We have to click on that. And here is where you're gonna see all the different labs and exercises. Okay. All we have to do now is just select which lab we're interested in. We're gonna go over lab number 3.
Also, while you are doing this, Elie, I want to remind that we put online the virtual machine that we're using. So the virtual machine is available in the website.
You can find it under the resources table. That's the first link here. It's taking some time. I will try to redo that.
Robert, is my assumption correct that you might either use the VM or the NDG platform to complete all the labs? That's correct. So you can download the virtual machine and do the labs in the virtual machine. Typically, I know I'm trying to figure out why it's taking so long to get the virtual machine. Typically, it's happening in few seconds. And also, Robert, the lab manuals are online. Elie, do you want to show where the lab manuals are in case that somebody want to just download the virtual machine?
Yeah, certainly. So in our website, if you go to the top, there is a page called Cyber Training. So you can go there and basically you'll find all these labs. There's a one single PDF file that contains everything here. So if you click here, you will find all these different labs and their exercises, and you're gonna be able to go over them if you decide to have your own machine running locally, and if you don't wanna use the platform. I think now this is ready. So this is what looks like whenever you do the reservation for a given lab. You will see a pod. In our lab here, we only have one device. This is the client. And within that client, we'll be starting Mininet and creating the whole environment where we have a switch and hosts and basically do the whole lab. Now, what we have to do is, you can see here also there's a button called content. This is where we can see the actual content of the lab. So you can open it in a new window. And I typically like to put them aside so that basically we can see the content and at the same time we can go over the lab. So on the left-hand side here now you can see this is the lab content. So first we have a table of content. In all the labs you will see a short overview. What are the objectives of the lab? And there's a table that contains the credentials. So for instance, sometimes you might run a command with higher privilege, you would need the password. So you would see it here, which is a password all caps. And then we have the roadmap. We start first by describing the theory behind the topic. For instance, here we are talking about the PISA architecture. And then we keep continuing with all the theory that we will plan to go over through the hands-on part later on in this lab. So all of this is what we were talking about in the slides. And actually in section 2, this is where the actual hands-on start. Okay. So now I will start by going to the client. So you can click on client. And from there, we will start by following the steps here step by step. So the first step, step number 1, we have a shortcut to Mini-Edit, the program that it's a graphical user interface for Mininet, and it's on the desktop. So all we have to do is launch that program. And now we are asked for a password. The password is password, all small caps. And now we can see that Mini-Edit is running. We can start by deploying some switches, some devices. But what we're going to be doing, we're going to be using the topologies that we already created for each lab. So each lab will have its own topology file. And since we are doing now lab number 3, we'll start by opening this lab. So file, open, I'm going here in step number 2, and then lab 3, and we have lab3.mn. This is the topology file in Mininet. And we can see now that it's showing our topology, which consists of a P4 switch and 2 end hosts. The next step is to start the emulation, start all the devices here, and we do so by clicking on the run button. So whenever you click on run, those buttons here should be grayed out. It means that now the topology has started, the emulation has started. We can actually start now using those devices. So in step number 2.1, we're gonna now see how we can execute a command on a certain host. So in this case, we will open the terminal of host H1 and perform a simple connectivity test using ping. So to issue a command on a certain host, in this case H1, we right-click on the host and we hold the right-click, and then we select terminal. And this is going to open for us a terminal, which is a Linux-based terminal. So all the commands that you would typically type in Linux can be executed here. You can use ifconfig to see the interface. You can use ping, any kind of command that you are interested in. One thing I have to mention as well is that the IP addresses are already configured within the topology. So host H1 has the IP address 10.0.0.1 and H2 has 10.0.0.2. And now what we're trying to do in step number 2 here is send some ping from host H1 to host H2. So I will start by typing this command, ping 10.0.0.2 -c 4. It means that I want to send 4 packets, 4 ping packets. And what we can see here is that there is no connectivity, which is expected in this case. And the reason is our P4 program is not deployed yet. There's nothing on the switch that will start doing the actual packet forwarding. And that's why simply we are dropping all these packets. Okay. Now in section number 3, we will iterate over the components of the basic P4 program, and we will see also the whole development environment. We will start first by launching a terminal by clicking on the icon on the desktop. So we can minimize those, or we can click on the show desktop button here so that we minimize everything. And then we double click on terminal. So we are now doing this step here. Then I will type this command, code. Code is the program that will be used to modify the P4 program. And I will pass as parameter to this command the lab name, the location of the files where this lab will be, or the ones that this lab will be using, right? In our case, this is lab number 3. And once we do that, we will have the Visual Studio Code open. And I just want to describe very briefly here, what do we have once we launch the Visual Studio Code? We can see on the left-hand side, we have the file explorer. So basically all the P4 files, the topology, everything related to that lab, you would find it here. Now currently we are seeing basic.p4, that's our main file, and we'll be invoking other files as well. This is where we describe other components in the architecture. Here on the right, we have the editor. So this is where we're gonna write the program, modify the program. And on the bottom, we have a regular Linux terminal. And the reason we decide to use this kind of styling or the appearance of Visual Studio is because we will be modifying potentially a few files here within the same program. And once we do that, we want to, let's say, compile to test if everything is working well. So we can use this terminal here at the bottom to actually perform the compilation. Okay. Now looking at the first file that we opened here, basic.p4, we can see that we have some include statements. The first two are related to the P4 language. So this is the core.p4. And the second one is related to the architecture definition. In our case here, it's V1 model. So if you are working with Tofino, this is going to be different, might be TNA or something else. And other than that, we have some include statements. These are including the files that we created here. You can see here that we have the double quotes, pretty much similar to what we do in C, right? If you are using the user-defined files, we can include them and use double quotes. So in other words, this basic file now is including all these files that we will potentially use when describe our program. Next, I will go and look at what is the headers.p4 file look like. So we have a file called headers.p4. I will click on that. And what we can see here is we have a few things to notice. First, we have some constant definitions. So I'm telling here that type IPv4 is equal to 800. This is just a constant. You can define that here. We are also inserting some type defs. This is just to make the program more readable. So instead of saying that I want a field to be equal to 48 bits, I can write MAC address underscore T, right? So this is going to be used when defining these fields. And then I will start by listing all the headers that I'm interested in parsing and using in my P4 program. So for example, we are first starting with the Ethernet header. So we start by typing header Ethernet, and we describe here what are the fields that are inside the Ethernet header. Okay, so this information you can get it from basically RFCs, or a simple Google search for any of these standardized protocol will give you all the fields and how big each field inside the header, right? So here, because we defined the MAC address to be bit 48, it's as if we are saying bit 48 destination address and bit 48 source address. Now the ether type, which is a field that will allow us to determine what is the type of the next header, this is only 16 bits, so we define bit 16 and ether type. And we do the same thing for IPv4. So I'm sure many of you are already familiar with these fields. Specifically here we have the source address, destination address. These are for IPv4 as well. And you have other fields, for example, the TTL, the protocol, and so on. Also, Vladimir was mentioning that there's some metadata bus that will be traveling through this pipeline, and this is where you can copy some information from throughout this pipeline. And here we have it, but we kept it empty just for simplicity. We're not going to use metadata. And finally, we are combining these headers into a single struct, which we are calling headers. So we're saying that my headers will potentially be Ethernet and IPv4. Now, the next step is to look at the parser. So we have a file called parser.p4. And this is where actually we are defining how to parse packets that are coming to our P4 program. So the parser includes the headers because definitely we're going to be using Ethernet and IPv4 here. But basically what we can see here is that we just created a parser. We called it my parser. Okay, and this parser accepts some inputs. For example, we have the packet, the header, the metadata, and the standard metadata. And the parser, you can think of it as a state machine. So it has some states, and we will transition from one state to another. And this is how you define how you are doing the actual parsing. The parsers have some standard states. So there's one called start, and this is where the actual starting begins. Okay, so we have start. We are transitioning to another state called parse Ethernet unconditionally. So we are saying, as soon as we start here, just go to parse Ethernet, which we are defining here. Now in parse Ethernet, what we need to do is we need to extract the Ethernet header. And this is what we are doing in this line. So packet.extract header.ethernet. And then we are checking the ether type field in the header. If it is equal to the value of the IPv4, Then, so we are checking this here. Then we go to a state called parse IPv4. Okay, and the default, so in case it's not equal to this value, we'll just accept and then move to the next block in our pipeline. Now going to parse IPv4, this is where we're gonna extract the IPv4 header and then accept so that we go further the pipeline. We have another file, ingress. This is where the control block for the ingress pipeline exists. So we can see here we have some information. I will not go over these because there are other labs that are specific for this purpose. But I just want to mention that the name that we use here for defining this control, we will be using it later on whenever we start the whole pipeline. Okay, so in this case, this is my ingress. For the parser, we used my parser, and so on. Next, we have an egress file for the egress pipeline. Here it's empty. We don't have anything in the egress pipeline, and we called it my egress. So we are in this step now. Then we have a checksum file. Also, we can see that we have two actual checksum here. First is the verify checksum, and then the compute checksum. Okay, and also these will be used later on whenever we start the pipeline. Now, finally, we have a file for the deparser, and that's the last component in our pipeline. This is where you specify which headers you want to emit. We call it here my deparser. Now, all these files that I showed you, basically, this can be considered like a template. So in most P4 programs, you would have very, very similar structure. And it's about what you write inside these controls and these parsers is what make your program different than the others, right? So you don't need, obviously, like to memorize all this stuff. This is like a template, a skeleton program. You can use it and then start adding on top of it. Now, going back to the basic.p4, because this is our main program. This is our starting point, right? I click on basic.p4. So we are in step number 1. And now the second part is to actually insert some piece of code that will actually start a new instance of this switch, right? Of this V1 switch. And we will insert it below the comment here. Okay. I will type the text that you see here, the code that you see here. So V1 switch. And then inside it, you can see here that we are defining them sequentially as they are defined in the pipeline. So we start with the parser, which we called my parser. And then we have my verify checksum. This is basically if you want to verify some checksum for the packet, if you want to drop it so that, you know, if it has some invalid checksum, you are doing it at the beginning. Then we have the ingress block, which we called it my ingress. And then we have the egress, which we called it my egress. And then we have my compute checksum. And this is where we actually update the checksum because you know that before programs most probably will do some header modification and you want to make sure to recompute the checksum so that your packet remains valid. And finally, we have the deparser, which we called it my deparser. Okay, and we give it a name here, main. So basically you can consider this as the main function in a certain C program that will start invoking other functions as well. Okay, now once we write this piece of code here, it means that our basic will actually use whatever we included in those files to start an instance of our P1 switch. Now, once we finish writing, it's very important to save the file, right? And in Visual Studio Code, you can see here that's showing this black circle. We want to make sure we save it. You can use Control S or File Save. Once it's saved, it should disappear. This means that your program is saved. Now going to step number 4, we're going to start by compiling the program and loading it to our switch. So the compiler that we use is the P4C. This is the reference compiler. This is a standard compiler, very well known in the community. So all we have to do is just type in P4C and the program name, which is basic.p4. And once we execute that, if we had some syntax error, they should appear here in the terminal. Otherwise, your compilation was successful, and you will see that some new files were generated here, specifically these two files, basic.json and basic.p4i. What we care about at this point is only the basic.json, because this is the file that really describes what the data plane is doing. So this is the file that will be used by the BMv2 switch to describe the data plane. This is, if you are using, for example, other architectures, it might be a binary file, or it might be any kind of file that will be accepted by that target switch. For this software switch, BMv2, it's a JSON file, and it's called here basic.json. Usually it depends on what name you provide for your main P4 file. And this is going to be used as a prefix for the output, and the file type is a JSON file. So now we did the compilation, we have this output, but it's still on our local device. The next thing we have to do is we need to push it to our switch S1, which we started in Mininet. And we already provided a script. This is a very simple script that is just copying this file to the file system of the Docker container, which is running the software switch BMv2. So push to switch basic.json, and then the switch name. This way, if you have multiple switches, you can push them to multiple switches, or you can push different programs to different switches. So it's asking us for a password. Again, the password is password, all small caps. Okay. Now we will verify that our file is now in the switch, and we will see how we can start the switch with that file. So we will go back to mini edit. We will maximize it from here. And to be able to go inside our switch, we will do the same thing as we did with the host. Right click on the switch and then click on terminal. Now we are inside the terminal of the software switch. Here, this is actually like a software switch that is running on an Ubuntu Linux. So same thing, we can issue any kind of command here, basically. And we can use ls to verify that our file that we pushed, the basic.json, is now inside the file system of our switch. Okay. Now that we know that our file is there, we need to start configuring the switch and give it this file as input. But before we do so, we want to make sure to allocate the interfaces to that switch. We are probably all familiar with the ifconfig command, which allows us to see the interfaces on Linux. So I typed in here ifconfig, and you can see that we have a few interfaces, one for management, a loopback interface. And also we have S1-ETH0 and S1-ETH1. And basically those are the interfaces that will be used by the software switch. Now, at this point, we will start our switch and allocate the interfaces. Okay, so now I'm in step 2. If you look at this figure here, 28, what we are doing basically is telling, whenever we start the switch, that I want S1-ETH0, this interface here, to have the port number 0 on my switch, and the S1-ETH1 to have the port number 1 on my switch. Okay, and we can specify that once we start the switch, as we are doing here. So to start the switch, we simply write simple_switch. This is the target of BMv2. -I for interface, 0 at S1-ETH0. It means that port 0 is now S1-ETH0. And then -I 1 at S1-ETH1. Now, obviously, you can allocate any kind of interfaces for that switch. Depends on the topology that you are trying to do. Now, another parameter that we are passing is this nanolog IPC and some file location here. And the idea of doing that is that because we want the switch to enable logging. So our goal is to see what is happening inside the switch. We want to see the packet as it traverses through the architecture, our V1 model architecture. So to do so, we instruct the switch to start this logging by using --nanolog, and we give it the file. Basically, this is working over IPC, inter-process communication. So you give it the location of the file, tmp bm-log.ipc. And now the most important here is to specify our compiled data plane, which is basic.json, right? This is what we pushed from the Visual Studio. And finally, we use and here just so that we run it on the background. We run it as a background process. Okay. And I will hit enter here. You can see that it told me that we allocated these interfaces as port 0 and port 1. Next, we will load some rules to the switch, and those rules are from the control plane, right? We didn't see them yet. We didn't see how they are, but basically you would need to populate the tables, as Vladimir was saying in his presentation. And this is done through the control plane. So we want to make sure that the tables that we have in our program are populated. For now, we were just going to use a script, but there's a lab later on that will describe exactly how we can populate them with values that we want to insert in our switch. So first, I would press enter here. So this is step number 1, to go back to the terminal. And then I will populate the tables by using simple switch CLI. I pass to it some file that contain all the rules, and it's located in lab3 directory. It's called rules.cmd. Basically, you would have a different directory for each of those labs. We hit the enter, and we can see that some entries were added to the tables. We're not going to discuss them now. We will discuss them later on, but just we need to understand that now the tables are there, are populated. Next, we will start the program. This is the nano message client that will allow us to connect to the switch to see what is happening there, to see the logs that are generated by the switch. All we have to do is just type in nano message client.py. And this is gonna connect to the switch. It obtained this configuration file. And now all the packets that arrive to the switch, we will be able to troubleshoot how they are passing through our switch, through the pipeline. We can see them here. Next, step number 2 here, we will start a receive program on host H2, because what we are planning to do is to send a packet from H1 to H2. So we can start, this is a simple Python program that just uses Scapy to print some information about a packet that is received. And it uses, sniffing on the interface that a certain device has, right? So if I want to open it on host H2 terminal, this is step number 2. I will right click on H2 to open its terminal, and then just execute receive. And you can see that now it is sniffing packets on the port or on the interface H2-ETH0 in host H2. Next, I will send a packet from host H1. So this is step number 3. I will go back to H1, which you already have it open here. And we will use a script called send.py, also a Python script. It accepts as input. The first parameter is the IP address, destination IP address, and some payload that you want to add on top of your packets. So let's say hello world. And we hit enter. So what we can see here is the output of Scapy, just telling us how the packet looks like. It has an Ethernet header, followed by an IP header, and has also TCP. And at the end, we have some raw payload, which is hello world, that we pass through the command line. Now, we can see here on H2 the same packet arrived. It means that the switch is doing the forwarding. But now, most importantly, let us inspect the terminal of the switch to see what happens there. So I will go back to the terminal of the switch. This is the behavioral model here. Okay, and what we can see here is this is where it starts. So we have a packet in, a packet was received. It was received on port 0. Remember, this 0 is the one that we use when we started the switch, right? From S1 ETH0. Then the parser started, right? It performed extraction on the Ethernet header and extraction on the IPv4 header. Okay, then the parser finished execution. And then now we have the pipeline start, which is our ingress pipeline. There we have some tables, which it didn't show, but there is a table that was hit and some actions were executed. Then the pipeline here ended, the ingress pipeline. After that, we have the egress pipeline. But as we've seen, the egress pipeline is empty, so it just started and finished. We didn't have anything inside that pipeline. And then we have the parser. So the parser started. There was some checksum update executed. And then we start by emitting the headers that we are interested in. If you remember, when we checked the my parser, we had the emit Ethernet and emit IPv4. So it's showing us exactly here what headers it emitted. Then the parser finished execution and the packet was sent out of port 1 so that it's forwarded to the host H2. So this is a very important thing to have whenever you write the program, because potentially before program can get complicated. And because they enable those in-network application, the goal is not only just to forward, you might want to do more complex stuff. And logging is a key feature to understand where is your packet currently in this pipeline. Is this table hit? Maybe you would think that why is this condition not being executed? But here you will actually see that there was hit or there was miss, or which kind of pass a certain packet took inside the control block, and so on and so forth. So it's important to have these available so that you can troubleshoot better your program. And this basically concludes lab number 3. So in summary, we just saw the development environment. We saw how we can compile, push the output of the compiler to our switch, start the switch daemon, allocate the interfaces, send a packet, verify that it's received on the other end, and see that all the different components in the architecture were executed as we defined them in our main program. Dr. Jorge, shall we have questions now, or?
Yeah, let's see if there is any question. Thank you, Elie, for the presentation.
Yep.
Well, we wait in case there is any. Elie, do you want to mention the importance of logging, looking at how the packet traverses across the pipeline? We're using BMv2, but in a Tofino environment, this is also available. Do you want to talk about that and how important it is for the deployment of real protocols?
Yeah, certainly. So basically, when you work with hardware, there's a lot of the hardware process a large amount of packets, and it has very high rates. So the logging will not be available as you have it, for example, in the software implementation. And that's why for Tofino, you have two variations. You have the hardware. This is the ASIC. This is the actual switch. And you have the software version of it, which is called Tofino model. Now, in Tofino model, because it's a software switch, it's not designed to be used as a production grade switch. It offers all these kinds of logging. So if you are writing a program that you want to deploy on your hardware, you are still able to see what happens inside the switch when you run it on a Tofino model. Okay, and there's another point that I want to highlight here in this lab. The software switch that we are using, BMv2, is not production grade, which means that you can use it for simple tests like this, experimenting, learning the language, trying new applications. but you cannot make it run at, let's say, 40 gigabits per second. You cannot run it at high rates. I believe the best we could achieve with BMv2, based on what we tried before, was up to 1 gigabits. But that was like the best case scenario. And if you would like to get to that level, you would need also to disable logging. Not only by not providing this parameter that we saw here when we started the switch, but you have to recompile BMv2, and there's some flag that will tell it that I don't want logging at all to be enabled. And this is very, very important if you want to get higher speeds. Otherwise, you're gonna get very, very low packet processing rate. And again, this debugging will allow you to make sure that your program is running well. Later on, you might want to perform some more tests because those programs will be used in production networks, and you need to make sure that it's working well. And there's ways to test the program. There's the framework PTF. This is the unit testing framework, packet test framework, specifically for P4. It can be used for BMv2 and Tofino, right? But this is very important, and you don't want to have a program that's kind of working or a little bit buggy to deploy it on a network, because that can have a lot of problems later on.
Thank you. And Elie, there is a question. I will read. What is the purpose of the command line command again? Is it necessary in the exercise, or will it be discussed later? I believe this is referring to the control plane command line interface. I think you have a slide on that, your presentation.
Yeah, so let me check here. So basically the CLI, simple switch CLI, this is just a command that you would use to insert entries inside your tables and to manipulate data plane objects in general. Now, if you want to perform switching or you want to do forwarding, you want to make sure that the tables that you have, let's say you have a table that will match on the destination IP and forward the packet from device A to device B. You want to make sure that it has the information there. It has what we call the rule that will tell it, if you receive a packet that's sent to this specific destination IP, use this output port, right? So you need to insert those. Those happen from the control plane, right? And basically, we are here in this lab specifically, we are just pushing two rules, very simple ones, saying that if a packet comes from port 0, forward it to port 1, and if it comes from port 1, send it out of port 0, right? But if you don't add those, then you won't be able to, if you have a table in your program, you won't be able to do some matching on that table to forward the packet.
Thank you, Elie. There's also other questions. I see the type of arguments in the parser or deparser, in, out. What is the difference? Yeah, so those are what they call the directions. And basically, there are some things that you can't modify. This you would use them more in when you manipulate, for example, registers. You can decide whether you want to register, whether you want to modify it or not. But basically, in out means that it's going to be used to be read and modified at the same time. And in, it means you are only reading, you're not modifying it. And out means that you might be modifying it as well. There is a second question, is we include the header field. However, how did we use the extracted values? That's a great question. In this specific lab, the goal was just to show the whole program. Typically, when you want to parse a certain header, right? Let's say you are parsing IPv4. The goal is to use the fields of the IPv4 header later on in your program, right? But in our case here, we did not use it. But if you are, let's say you want to decrement the TTL or you want to modify something in the IPv4, you need to parse it. The goal was just to show you how the parser looks like and how you can go from one state to another one. But eventually, if you would like to use a certain header, you would need to parse it. Thank you, Elie. I don't see any other questions. So what we will do is right now it's 4:05. We will have a 5-minute break, and then we will have our second hands-on session. We will start at 4:10 p.m. Eastern time. So we'll have a break right now.